29th, 2020. It's a beautiful spring day out there. I hope you're all doing well. It's been a little bit since I've made an original video for you. Thank you for the hard work. I really appreciate it. I know this is very different, but we're getting through it. We're going to do a very concise boiling down of a skill that you heard about last week, electron configuration, today. But first, I want to share with you a bit of a change to how things are going to work. We will now have a mandatory Google Hangouts every Tuesday starting next week. You can see it here on the schedule. I've updated the needs to know as well. And this mandatory Google Hangout is something that Mr. Grant asked that all teachers do for all classes. I'm going to keep it brief. It'll be about 15 minutes, I think. We'll have a chance to just say hello, ask an attendance question, maybe reconnect. I'll do an overview of the week, and then you can ask any questions if you have them. It'll also be used to do attendance, so please make sure you be there, and if you can't, you're reaching out and letting me know why. And that'll be only on Tuesdays. I'm going to keep the Thursday Google Hangout as an optional one for you to pop in and ask questions about assignments, as we've been doing in the past. All right, so without further ado, you watched a video last week on quantum mechanics, which had a lot in it. The skill I really want you to be able to do is write electron configurations. It's another very important skill in chemistry for atoms and ions. And this video is going to kind of boil down quickly how do you do that and what are the most important need to knows. I also would like you to be able to draw Bohr models of atoms from electron configurations, although I do not ask you to specifically do that in the assignment, just because of how challenging it is to draw in Google Docs. And then lastly, I want you to be able to determine the number of valence electrons of elements and ions. So let's get into it. Recall that the quantum mechanical model of the atom is the current model of what the atom looks like. You did some history on atomic structure that went through various stages of what we thought the atom looked like, and this is where we're at today. In this model, the nucleus is a very tiny central part of the atom, and really what we're concerned with here are electrons. It's the idea that electrons exist in very specific regions, shapes at certain distances from the nucleus because of their wave-like nature, and electrons are the majority of the space in an atom, the majority of the volume. Here's an image of a quantum mechanical model where each of these different colored clouds represents different electrons orbiting at different distances and different shapes. And so how do we represent this? We don't draw those complex pictures often. Instead of drawing those pictures, scientists write what we call electron configurations to represent what an atom looks like, which systematically tells you how many electrons are in each region. So for example, here's lithium's electron configuration. We'll be coming back to this one a lot as we go through the next few slides. It reads like this: 1s2, 2s1. And each element of the electron configuration has meaning. So an electron configuration is made up of three parts. There's energy levels, orbitals, and electrons present. The large numbers are the energy levels. So this one here represents the first energy level. The orbitals are represented with letters. That's what this S is representing, the S orbital. And then the electrons present are represented with exponents. So here the 2 says 2 electrons. So when I read 1s2, 2s1, I'm thinking lithium, this atom, has in the first energy level, in the s orbital, 2 electrons, and then in the second energy level, in an s orbital, 1 electron. So we're going to break down each of those parts. First off, the energy levels. Energy levels can be thought of as distances from the nucleus and are represented with the full size numbers. The higher the energy level, the farther the atom is from the nucleus. And we kind of already talked about energy levels back when we did the Big Bang unit and we talked about emission spectra and how those were created, it was by electrons transitioning from low energy levels to high energy levels, taking in energy, and then as they fell back down to the ground state from that excited state, as they fell from a high energy level to a low energy level, they released that energy as a specific color of light. So hopefully this concept of energy levels is familiar from that. You can see here in this Bohr model of the atom, we have a lithium atom again. I know that because it's got 3 protons. It's also got 3 electrons. And what you can see is this first energy level closest to the nucleus has 2 electrons in it. And then in the second energy level, we have 1 electron, which is just like what the electron configuration tells me about lithium. So this concept, like I said, comes from that previous model of the atom, the Bohr planetary model, which was then later replaced by the quantum mechanical model. And in that replacement, one thing that is important to note is that the energy levels are actually 3D. They're not 2D as often represented in the Bohr model. So here in this Bohr model, it is like planets orbiting around the sun in kind of a plane, but in actuality, electrons are orbiting around the nucleus in 3 dimensions, which is what this image is trying to get at. That inner orange circle is the first energy level, the blue sphere is the second energy level, and then the orange outer sphere is the third energy level. So we just covered energy levels. Think of those as distances to the nucleus. Now we'll get into orbitals. Orbitals should be thought of as different shapes that electrons can orbit in and are represented with the letters S, P, D, and F. Those stand for sharp, principal, diffuse, and fundamental, if you're curious. S, P, D, and F. And here in this image, you can see those different possible orientations. S is just spherical, but as you move into the other letters, the shapes get more complex. So P I kind of think of as like dumbbells, and then I don't even know what I would call D and F. Not all energy levels have all the orbitals. So for example, the first energy level only has room for the s orbital. As you get to higher and higher energy levels, you start to access more orbitals, more different shapes that can exist. And then each orientation of an orbital can only hold 2 electrons, one that spins clockwise and one that spins counterclockwise. That is referred to as the Pauli exclusion principle. And you'll see that the s orbital has only one possible orientation, and therefore it can only hold at most 2 electrons. The p orbital, on the other hand, has 3 orientations, one in the x direction, one in the y direction, and one in the z direction. And because each of those orientations can hold 2 electrons, 2 times 3 would be 6 total possible electrons in the p orbital. D has 5 orientations, each holding 2. 5 times 2 is 10. And finally, F has 7 possible orientations, each holding 2, makes for 14 possible electrons. This is an important table to have access to, and I'll show you a link to a cheat sheet that I built for you that has this table on it when it comes to writing electron configurations. All right, and then the last piece of electron configurations we said is number of electrons. How many electrons are actually there? So the number of electrons in a particular orbit at a particular energy level is noted with an exponent. So like we said up here in lithium, the big one represents the first energy level, the S represents the shape that orbital is in, and then the exponent 2 represents how many electrons are there. So again, I would read this as, in the first energy level, close to the nucleus, in a spherical shape called the s orbital, there are 2 electrons. The electrons of any atom fill in a very particular order of increasing energy, which is called the Aufbau principle. Aufbau is German for building up. You start at the bottom and you build up. And that order is written down here to the right. So this is the other half of the cheat sheet, is the order. The first half of the cheat sheet is how many electrons you can put in each orbital, and then the second half is the order that you fill in. And you'll note here that it starts at 1s, it moves to 2s, and then 2p, and then 3s and 3p, and then 4s, but then it jumps back to 3d. And that's just because of the nature of the universe. So it is important when you go to write electron configurations that you reference this order, because some weird things do happen. Sometimes you'll fill a higher energy level and then jump back to an orbital of a lower energy level. And you can see that represented here with this arrow diagram as well. I would read this by kind of following the zigzag arrow through. For the sake of this class, we're not going to get up into really complex atoms at the bottom of the periodic table. So I would imagine we'll at most deal with electron configurations going up to 4p. So really you only need the first part of this. And note that, this is super important, you cannot put more electrons in an energy level and orbital than that orbital can hold. And that's where we reference back to that previous table. S can only hold 2, P can only hold 6, D can only hold 10, F can only hold 14. So how do we actually do this? We have a procedure for building electron configurations. It's written out here in 3 slides. The very first step, which is super important, is to determine the number of electrons in the atom. And then your electron configuration that you end up with must account for all of these electrons. So I'm going to go through an example question. My example question is, what is the electron configuration for a neutral chlorine atom? And to figure out how many atoms it has, or how many electrons it has, I need to reference a periodic table. I would see that chlorine's atomic number is 17. That means it has 17 protons. But if I know that it's neutral, its charge is 0, then it must also have 17 electrons for all the positives to cancel out all the negatives. So I determined from my periodic table, from the atomic number, that chlorine has 17 electrons. I keep that number in the back of my head because that is the ultimate number that I want my electron configuration to get to. All right, so next, the fun starts, and I'm actually gonna remove myself, if I can, from the screen. That might not work, or maybe it does, I'm not sure. I still see myself, but maybe you don't see me right now, so that you can see the example. But anyways, what we do is you can open the electron configuration cheat sheet right here, it's linked, and you'll keep in mind a couple things. As you begin filling subshells, orbitals of energy levels, using the facts from the previous slides. Keep track of your total electrons accounted for as you go. And some things you need to keep in mind. You need to continue until you account for all the electrons of the atom, in this case 17. And certain subshells can only hold a certain number of electrons. This is dependent on the orbital, S, P, D, or F. Do not overfill those shells. And then lastly, electrons fill shells in a particular order. Use that order from the previous slide, the Aufbau principle. So hopefully you can't see me up here. I still see myself, but the very first way I'm going to start out here is chlorine will fill the 1s subshell with 2 electrons. Why do I say 2? Because an s orbital can only hold 2 electrons. So far what I've got in my electron configuration is 1s2, and I've counted for 2 total electrons. Next, I'm moving up that list. Chlorine will fill the 2s subshell with 2 more electrons. Again, 2 more because that's all an s orbital can hold. So then I've got 2s2, which accounts for, with the 1s2, a total of 4 electrons. Next, chlorine will fill the 2p subshell with 6 electrons. That means I'm up to 2p6, which is a total of 10 when I count back the 2 previous s subshells. I still haven't hit 17, so I've got to keep going. Chlorine will fill the 3s subshell with 2 more electrons. Now I'm at 3s2. for a total of 12 when I count the 2p6, the 2s2, and the 1s2. And then lastly, chlorine will not fill the 3p subshell in total, because if I put 6 there, that would account for 18 total electrons. Chlorine only has 17 to distribute, so I'm only going to put 5 electrons into that 3p shell. So 3p5 would get me up to 17 total electrons when I add it to the 12 total I had previously distributed. I hope that process makes sense. It's something that'll definitely come with practice and is super important for where we're going next. So the final step here, see if I can put myself back in the shot. Maybe I just reappeared. Step 3 is to write all of the subshells, the energy levels with their orbitals, together, starting from the beginning and including those exponents that you came up with as you went through the list. You know you're done if the sum of the exponents equals the total number of electrons in the atom. So the electron configuration of chlorine I would write is 1s2, 2s2, 2p6, 3s2, 3p5. When I add all of those together, 2 plus 2 is 4, plus 6 is 10, plus 2 is 12, plus 5 is 17. The sum of my exponents, 17, equals the total number of electrons I decided in step 1 I needed to account for. No subshells are overfilled. What I mean by that is each S has 2 and each P has 6 or less. Again, we stopped at 5 here because if we put 6 in there, that would have been 18 total electrons, which is more than we had to distribute to this chlorine atom. And lastly, the subshells are in correct order, and so we're done. Last slide I have for you here is about Bohr models and valence shell electrons. I'm going to keep going with this electron configuration of chlorine as an example, which we just said was 1s2, 2s2, 2p6, 3s2, 3p5. Bohr models of atoms can be created from electron configurations by creating rings for each energy level and filling each ring with the total number of electrons in all orbitals in that energy level. What I mean by that is I can look at this and I can say, okay, in the first energy level, there are 2 electrons. And so I'm going to draw a ring close to the nucleus, which here is just represented with a solid circle. I can draw a ring and I'm going to put 2 electrons there to represent those 2 electrons in the 1s2 spot. And this particular diagram goes as far as to draw those 2 electrons as light blue to represent that they're from an s orbital. Now I go up to the next part, which is 2s2, 2p6. These total 8 electrons are existing in 2 different orbitals, but they're in the same energy level. They're at approximately the same distance from the nucleus. I know that because they both have a 2 in front of them. And so I would draw another ring that would be the second energy level. And I would draw, in this case, 2 light blue ones to represent the 2 from the s orbital. And then I would draw 6 light green ones to represent the 6 electrons from the 2p subshell. And then lastly, I'm going to draw another ring for the third energy level because my electron configuration includes the third energy level. And I would draw 2 light blue ones for the 2 in the s orbital and 5 light green ones for the 5 in the p orbital. And that's why you can see there's 1, 2, 3, 4, 5 light green ones. Again, if I count all those dots, they're going to total to 17, which is the total number of electrons that this chlorine atom has. The outermost energy level is the valence shell. The valence shell is super important in chemistry because that is where chemical bonding happens, where reactions take place. Those electrons on the outermost energy level are what touch other atoms with their electrons on the outermost energy level. And then lastly, the valence electrons are the number of electrons in that outermost energy level. So in this particular example of chlorine, from my electron configuration or from my Bohr model, I can determine that the valence shell, the outermost energy level, is 3, the third energy level, and there are 7 valence electrons in that energy level. Tricky thing here is don't get caught up by saying there's 5 valence electrons. You have to still also include the 2 from the 3s as well, because both 3s and 3p are in the third energy level. I hope all that made sense. I'm going to turn it over to you now to give it a shot with an assignment. And again, please reach out if you have any questions, any comments, any feedback on how things are going. I hope you're doing well, especially as it's starting to get nicer outside. And again, please be there in your 15-minute time slot on Tuesday morning. Thank you very much, guys. Be well.